All right, so now we move on to lesson 25, which is the second lesson of Unit D, and it's the second part to simple harmonic motion, which is springs. So in lesson 24, we started off with pendulums and we dealt with how simple harmonic motion is represented in pendulums. And very similarly, what we're going to do is now shift that to be simple harmonic motion, but in the case of springs. So there's a couple major differences, but overall, there's a lot of similarities between the two. Now, when we look at the springs component of simple harmonic motion, we're going to be looking at weighted springs. And weighted springs bring up Hooke's law, which is on your formula sheet. And it's this idea in which we can relate the spring constant and the displacement to describe a resultant force or a spring force, or what we call from pendulums, a restoring force. Now, in a simple example here, what we can look at is, let's suppose that some sort of tire gauge is being attached to a tire, and what we're trying to do is either measure the air or put air into the tire. In this case, we're trying to measure the pressure or the pressurized air that is released from the tire to see, hey, how much psi or how much is it inflated? What is the overall pressure gauge registering as? So the way that these work is you're going to put it onto the tire valve. The tire valve will then disperse air from the tire into the pressure gauge, and the pressure that's generated in this will pressurize and force the spring by some amount of distance out on the other side. And depending on how far it displaces this bar on the outside, this is going to indicate what the PSI of the tire is or what the pressure in the tire is. So it's a simple example of how we can create some sort of force on a spring, which then results in some sort of compression, which can then push some sort of distance outwards on the other side. Now, would I ever ask you specifically about this example? No, but it's just one of those applications in which we can see I can take some sort of force and apply it to a spring, and this is going to result in some sort of measurement that we can get out of these things. Now, let's get specific on Hooke's law. Hooke's law is this relationship between the spring constant and the displacement of a spring, and it simply says, if I want to talk about the restoring force, which is this Fs, in pendulums we called it Fr, in springs we're going to call it Fs, this is the restoring force, and so I'm going to put Fr here, which is equal to the spring constant times the x value, which is the displacement. Now again, the spring constant is how much force it takes per given meter of material, and we can tell that even by the units here. When we look over at the units, it's newtons per meter or force required per meter of that material. And then when we look at the x, it's how much the spring is either compressed or stretched away from the equilibrium point. So that's very critical here. Now, you're probably like wondering, what is this negative that's attached to here? Why is there a negative up front? Well, the negative is going to help us understand how the restoring force is always pointed towards the equilibrium, and we'll see that throughout the notes, but we want to be specific with that. Now, at the very bottom of this page here, again, just as a reminder, the spring constant is the stiffness of the spring. So we can look at different springs, and they may all have different constants. Like the one that comes to mind right away, speaking of cars in that first part, is what would the spring constant of a car's suspension be versus something like a pen, as you click it up and down on a simple pen that you would write with? Well, clearly we know the spring constant would be way greater on a car than it would be for a ballpoint pen, because for a ballpoint pen, we don't need a lot of force in order to activate the pen. But for a car, if the spring force was, or spring constant was very little, what we would find is that the car would just collapse and that the suspension would break, which we don't want. We want the car to be able to handle a bunch of bumps and little divots in the road. So the spring constant would be a lot greater for a car. Now, let's skip forward to example 6 here, and I want to take a close look at this one because in this lesson, we're going to take a close look at vertical springs versus horizontal springs. Now, first and foremost, when we deal with vertical springs, we need to analyze this from the point of view of the following. I want you to draw a line in this diagram that is horizontal right at the bottom of this resting spring, and the resting spring is going to be this one here. So on the left-hand side, if no mass is attached, that's what the spring would look like. And in fact, if this is where the spring would rest, we're going to write it as 0 meters in terms of the x height, or the x displacement, we should say. Now, if I attach a mass to this, in this case, I'm going to attach a ball that is 2.45 kilograms, it's going to stretch and then rest at that bottom position or rest at this position once that mass has been attached. So it's not oscillating upwards and down. In this example, we're specifically saying we attach the mass, it stretches, and it stays exactly where it is. Now, if that's true, we need to note a couple things here. First and foremost, in the margin, what I would like you to write is if I know that this mass is stationary by the law of inertia, or what we call first law, we know that the acceleration is zero, and that's due to the F net being zero. So if this object is stationary, its first law, F net is zero, meaning that Fs is equal to Fg. And this gives us a really nice problem solving ability, because if we know that our restoring force, or the spring force, is equal to the force due to gravity, or gravity, we really like this, because now it's going to open up this ability to solve for things like, what is the displacement? What is the spring constant? Maybe what is even the gravity that's dealing with these problems? It opens up a lot of things here. And so you really want to annotate that as, when we look at this 0.124, this is going to represent the x distance from equilibrium. And then when we have this, it's going to be stretched and it's going to pause at this point. It's not oscillating upwards and downwards. Now, let's get a little more specific about a new equation that we're going to add here. When we talk about vibrating or oscillating weighted springs, and we're trying to solve for the period of vibration, we're now going to have this new formula that comes directly off our formula sheet, and it's the following. The period is equal to 2 pi times the square root of the mass of the object over the spring constant. Now, we want to highlight something very specific here, and it's this. For an ideal spring, there's one condition we want to note right away. The mass of the actual spring itself is going to be zero. And so we don't want to consider it as having like, oh, it's a 5 kilogram spring, or it's a 5 gram spring. What we want to do is just null that and say, in an ideal spring, the only mass we're considering is the bob, or the actual object that is attached to the spring that makes it the weighted spring. The second piece of an ideal equation, or an ideal spring equation, is that when we look at this piece here, we're going to ignore friction and air resistance. So it might be important to note that there's no friction / no air resistance. We could also take this one step further and say, well, for this spring, there's no damping. And damping simply means that I'm not making contact with the spring. I'm not removing energy from this. So we're going to see that a lot when it comes to one-dimensional waves and two-dimensional waves, and even some of the Doppler effect. When we look at this, specifically with waves, when we bring up this terminology of damping, damping is no energy is being removed due to physical contact with external forces. Very critical. Now, as we look at this equation here, this vibrating weighted springs period of vibration equation that we've just established, we want to make a parallel to our last unit, or our last lesson, lesson 24, and say that the period of this, or the period, the t value that we solve, does not depend on the acceleration of gravity or the amplitude or vibration. So it does not depend on how far we bring it away from the equilibrium, or what the gravity is of this situation. And I mean, we can clearly see that directly in the formula. If I saw any amplitude here, I would see some sort of L, or some sort of, and not L, I would see some sort of A, meaning amplitude, or I would see some variable that represented the amplitude, like even we could say X in here, if it was really dealing with something dealing with the amplitude of that vibration. The other thing we don't see in the equation is G. Unlike in our other equation, where it's T is equal to 2 pi square root of L over G, which is the period for pendulums, pendulums definitely rely on the gravity and the length of the string. But in the case of this equation with springs, no way. We don't care about that. So you may actually even want to highlight this piece here, because in later parts, or one of the examples we're going to touch on, that note is going to become very specific and help us out with solving it and giving us a rationale as to why a certain property exists. All right, now let's flip our page over to here. This is where we're going to deal with horizontal springs. So we've dealt with the vertical springs, which they experience some sort of Fg in combination with an Fs, or a restoring force, and that can either be oscillating or stationary. A lot of the times it's stationary, but it could be oscillating. In the case of horizontal springs, we really want to make sure that we're understanding how position relates to what's happening with the given mass. Now, right away, when this thing is horizontal, there is no sort of Fg. We don't really, well, there is an Fg, but it's being balanced by the normal force that is the responding force vertically. So Fg and Fn are balanced. We don't need to include these things on a frictionless horizontal spring in our Fnet diagram or in our free body diagram. If you wanted to draw those things in, great, but if not, it's all good. What we're going to assume is that our Fnet, or the net force, is purely the restoring force that wants to bring it back to equilibrium, which gives us this really powerful tool, which is the following. We can now sub in mass times acceleration, which is equal to the Fnet, and by doing so, we can solve for mass, acceleration, the spring constant, or even the displacement of this spring from equilibrium. So it gives us a really nice, powerful tool, but you do need to recognize in the case of horizontal springs, the F net is the restoring force, just like it was in pendulums. The net force was the FR, or the restoring force trying to bring it back to equilibrium. Now let's look at the first situation here. So let's suppose we're to the left of equilibrium and the spring is somewhat compressed, because if it's to the left, it means that the spring is being compressed together. It's maybe they're going left or right at this moment, but for the case of this, we're going to assume that it's just somewhere on the left-hand side. Now, just like it says in the notes here, one thing we want to point out right away is the following. At equilibrium point, this is where we consider x to be 0 meters. And this is where the spring would naturally rest if we had no energy in the system and we just let the mass and the spring sit exactly where they would sit. So we don't introduce energy, it would sit at that equilibrium point. But in the case we did introduce energy and it's on the left-hand side, let's note a couple things. First and foremost, just like we do in math 20-1 or even 10 or 30, when we're to the left of equilibrium or to the left of the origin point, these are all negative x quantities. And so I really want you to write that in as anything in this region is negative x. We now have a force that looks like the following. So one force, or the main force, is Fs. This is the spring force, and it is pointing to the right because it's trying to restore back to that equilibrium point into its natural rest position. The other thing we want to annotate in here is the acceleration. Because Fs is the F net, I want to now write the acceleration going in that direction because the net force determines the direction of the acceleration. Now, we look at this and we assume that both of these are positive, and just strictly by even the orientation of the x-axis, again, when we head to the right, it's positive. So the force and the acceleration are both positive. The displacement of x is negative because it's to the left of the equilibrium point. Now, this is one situation. We're to the left of equilibrium. These are the conditions we get out of this. What if we instead go to the equilibrium position? And let's say the mass is momentarily snapshotted at this position. Well, something that we really want to annotate is, again, the x is equal to 0, which is actually noted right there. So it's 0 meters, just to be very specific. And on top of this, there's a couple conditions we need to annotate here. If this is supposedly the equilibrium point, by the previous unit, or unit C, we also know that our kinetic, not potential, our kinetic energy is maximized. And if our kinetic energy is maximized, it is also the point in which the maximum speed occurs. And so if this is the maximum speed, then the acceleration and the force have to be 0, because if the object was still accelerating, this wouldn't be the fastest speed. And so at this point, we need to annotate a couple things here which are noted above. First and foremost, I'm going to put one dot and say the restoring force is equal to 0 newtons, obviously, because if I'm at the middle and that's where we're trying to restore to, then I'm not going to restore past the equilibrium point. So the force shouldn't point to the left or right. That wouldn't make sense for us. And then the other thing here is, if this is the maximum speed, it must be that the acceleration is equal to 0 momentarily at this exact position. So it's not saying the acceleration is 0 forever, just purely at this point, it is 0. And then once it makes it past this point, because the object has inertia, like let's just scroll up for half a second here. If I'm supposedly to the left of equilibrium and the object is zooming this way because it has some sort of restoring force and acceleration, by the property of inertia, or by first law, if an object was given some sort of overall speed or given energy originally, then it's going to want to accelerate in that direction, which it did. But more importantly, by inertia, it wants to continue its motion. And so even if the restoring force is 0 and the acceleration is 0, the object was given motion and it will propel through. So this is just a momentary snapshot of what's happening. So we look at this and I wonder if there's a more specific way of saying this. Yep, there's a couple notes here. So we're just going to read through this and highlight the most important things here. As the mass moves towards the equilibrium, the restoring force and acceleration decrease while the speed increases, because once it hits that equilibrium point, we have maximum speed. Now, as it moves through this equilibrium point, no compression or tension exists in the spring because it's at its point where it would naturally rest. And therefore, the restoring force and the acceleration are 0 when the speed is maximum. That is a very critical point for us to highlight. Now, we're going to go to our third and final situation. We had to the left of equilibrium, we have on the equilibrium, now we're past the equilibrium. So to imitate what we did before, when we look at this, our x is equal to 0 meters right at the equilibrium point, and then what we need to annotate here is that if my mass is to the right of this given situation, then these are all the positive x values. So I'm going to write this as positive x in this region, just like it would be in math 10, 11, 12. You're going to see this positive x value for all of these. Now, we want to annotate the following into here. So at this region, we have the following situation. We have a force or a restoring force that is pointing left. It wants to bring it back past or towards the equilibrium, I should say, not past the equilibrium, but wants to bring it to the equilibrium. And then on top of that, because the Fs is the net force, this means the acceleration is also going in this direction, which is the left direction. So therefore, we would say this is in the negative direction. Both of these are negative, the Fs and the acceleration. In combination, they're both heading to the left or towards the equilibrium. So let's make sure we highlight that from the paragraph or highlight any relevant information that backs that up. So once the mass is beyond the equilibrium point, it begins to stretch, and that stretch results in a negative restoring force and an acceleration towards the equilibrium point once it stretches past that equilibrium. The mass then slows down and comes to a stop very momentarily at the end, and then once it comes to a stop, it's going to want to accelerate back towards the equilibrium. And so when we look at this, just like the acceleration of a pendulum, the acceleration is, whoa, and I don't want to erase that, just like the acceleration of a pendulum, the acceleration of the mass spring system is not uniform. I can't emphasize how important that is. When we talk about the acceleration at any given point on this spring or on a pendulum, it's always different. And so if I was to go to my diagram here, whether it's this position or this position or even this position or this position, all four of these have different acceleration measures. And sure, you could argue that there's going to be some symmetry. So the acceleration right here might be equal to the acceleration here because they're equally displaced from the equilibrium. But overall, when we talk about the infinite options of acceleration, the acceleration will be different quite literally at every single moment that it passes along this journey of oscillating backwards and forwards or left and right. And so thus, in order to calculate any sort of speed or displacement or height, what we always do is use the conservation of energy, or what we do below this here, and I'm just going to make sure I really formalize this here, do not be afraid to use unit C. So I'm going to say use unit C, which means use conservation of energy. And remember this. So when we're using unit C and we're using the conservation of energy, there's maybe two ways you could approach this. The way that I showed in class was the following. Let's describe the sum of the initial energy equaling the sum of the final energy. So that's one way you could approach this. Or what you could do, and I've seen this lots before, because this is mechanical energy or this is potential and kinetic working together, you can write this as the following. The energy of the mechanical energy initially is equal to the mechanical energy in the final position. That would also be a good way to write that, but sometimes I like to write the sum of the energies because it can be one energy, it can be two energies, it could maybe even be three energies depending on the given situation, but we want to look at this and be like, it's the sum of the initial energies, or it's the initial mechanical energy equals the sum of the final, or the sum of, or I shouldn't say the sum of, but the total mechanical final energy. Okay, so again, if, and then I'm going to rephrase it like this too. If you ever need to calculate speed, like let's say it says the speed at this moment is blank, the height at this moment is blank, the displacement at this moment is blank, use conservation of energy. This is your free like invitation. It's words telling you, please use these formulas that we've learned in Unit C to help assist us in the simple harmonic motion solving for these problems. Because using simple Fs equations or Hooke's law, this isn't going to get you far. And even with the pendulum, you can use the period equations for both springs and pendulums as much as you want, but you're going to hit a wall where you can only solve for certain things using conservation of energy. And so this is where the two go hand in hand, and we need to be aware that we could be crossing back into Unit C just a little bit to help us solve these problems. All right, now let's go to some in-class examples here. First and foremost, we have this example where we have some sort of spring that's being hung and it stretches by 22.75 centimeters. What is the spring constant? Now, the way I read this is the following. I read this as, oh, once this string has the mass attached, it stretches and it pauses exactly where it is. So we're going to draw a diagram of that. Here's the vertical, let's call it the support if we really want to. We attach a spring, and so I'm going to try it neatly as I can, write a spring down like this. I'm going to draw the mass on the bottom, and this could be either represented as a box or a ball. It really doesn't matter. And then the one thing we're going to want to include on our diagram right away is the equilibrium point in which the object would rest if there was no sort of stretch that was given to this thing. So if there was no sort of energy given to this situation, if the mass didn't vertically pull on this, the spring would naturally sit there. Or you could even write it as this is the equilibrium position where the object would oscillate about. So this is x equals 0 meters, which we also call the EQ point. I sometimes just write it as EQP, or the equilibrium point. Now let's write our forces on here. In the downwards direction, we have Fg. In the upwards direction, we have our Fs, or the restoring force. So let's make sure we annotate both of those. Fg, Fs, perfect. And then the last thing I'm going to annotate here is, what is this distance we've just created? Or how far did the spring stretch? Well, because we had it in centimeters, 22.75, I'm going to write it in terms of meters. So this is 0.2275 meters. All right, now we have everything we need in terms of the free body diagram. We know exactly what's happening in terms of this looks like it's going to be the Newton's first law because it's going to momentarily pause or be hung at this point and left. So it's not vertically oscillating, or it's not going backwards and forwards at this point. It's not vibrating as we sometimes use in the spring terminology. So we're going to start the problem. Right before we do that, I'm just going to annotate one thing here, and it has to do with the mass. We look at this and we want to make our mass into kilograms. So I'm going to divide it by 1,000, and this is going to give me 0.5 kilograms. Okay, let's start the problem solving. By first law, we know that the F net is equal to 0. And I sometimes like to just write this in here just so we conceptually understand what's actually happening. This means that our Fs, or restoring force, is equal to the force due to gravity, which is equal to, by Hooke's law, negative kx. Now, because we're not solving for specifically the Fg or the Fs, what we're actually trying to solve for in this case is, what is the spring constant, or how stiff is this spring, the measure of stiffness. Now, Fs we don't know anything about, but we do know that Fg is equal to mass times gravity, which is equal to negative kx. And then from here, if we want to solve for that spring constant, I'm going to divide both sides by negative x, and this is going to give me the following. K is equal to mg divided by negative x. Now, we clearly know that k is not negative, and so this is one thing that's really important to annotate, is that we look at this and we're like, we shouldn't get a negative spring constant, or else something's clearly wrong with this. And so rather than just moving forward with this and maybe forgetting the negative, which, I mean, we could, what I want to do is think about what's actually happening in this problem. We could approach it from the two following ways. We look at this and we're like, okay, the equilibrium position is here. If I'm below equilibrium, this is like being below the x-axis. This is where we have negative x. It's below the equilibrium point. It's negative in terms of its displacement. So there almost should be a negative embedded in this x when we plug in our stretch factor. Now, the other way we could approach this is, we know gravity is a vector quantity, and if it's going down, in this case, it's also negative. So I'm going to give you the two options to do the following. And I'll actually write them both out because both would be valid in my opinion. You know, physicists might argue this, but I think that this seems okay. We're going to plug in 0.500 kilograms, and we're going to multiply it by, first, what if I put negative 9.81 meters per second squared divided by the negative, and then in brackets, we know the stretch factor is 0.2275 meters. This would be one way in which the negatives would cancel, because you see negative here, gone, we could get our value. I'm going to write out the other way. The other way would be the following. This is equal to, again, the mass doesn't change, so 0.500 kilograms, multiplied by, let's just leave g signless, 9.81 meters per second squared, rather than obsessing about that. We could divide this by negative, and because this is going down, or it's below the equilibrium, we can make this 0.2275, but negative. And then again, look what happens. The negative and the negative in the bracket cancel, therefore we get a positive. And so I'm going to leave it up to you. Whatever you feel more comfortable with, as long as you understand that the k value must not be negative, because it's just a constant. It doesn't have direction. It's not a vector quantity. It's scalar. So we want to make sure that there's no negative here. And therefore, when we actually calculate this, we get a K value, which is equal to 21.6 newtons per meter. That's how much spring force would be required for this spring to compress it by a meter. Okay, now let's move on to the next problem here. So in the next problem, we have an ideal spring, aka something that ignores air resistance, friction, dampening from a hand or some sort of external thing that's touching the spring. It's left to its own devices, it's given some energy, and then it's let to oscillate or go at its own will. Now, when we look at this problem, they ask us the following. An ideal spring requires 16.5 seconds to vibrate, or what we could consider oscillate, 25 times when a 200-gram mass is attached to the spring. What is the spring constant, and does it matter if this spring vibrates horizontally or vertically for this problem? Okay, let's break this apart. So we're just going to do the algebra of this, and we're going to ignore drawing this out purely because I want to discuss why it doesn't matter for this to be horizontal or vertical. We're going to discuss that specific factor. Now, first and foremost, they gave us enough information to find the period. So when I find the period, I'm just going to take the seconds, which is 16.5 seconds, and I'm going to divide it by the 25 cycles in which that happens during that time. Now, what you're going to find is that this is equal to 0.66 seconds. And if this is equal to 0.66 seconds, the other thing we may want to change here is the mass into 0.200 kilograms. Again, we do that by dividing it by 1,000 because we don't want grams, we want the standardized units of kilograms. Okay, we have the period, and now what we're going to do is, because we know the period, because we're looking for the spring constant, we're going to use the period formula that has been derived today in our, or maybe not derived, but has been provided in this lesson. And that is the following. T is equal to 2 pi multiplied by the mass divided by the spring constant. Now from here, we're trying to solve for the spring constant or the K value. So before we do that, what I even recommended when we dealt with the pendulum equation is divide by the 2 pi. Now this isn't the only way to solve it, but it's a way of avoiding forgetting to square this 2 pi that's given here. Because what might happen is if you don't do this and instead you just square both sides, you may forget to distribute this by power rule. So we're going to just divide away 2 pi, put it over on the other side, and it's going to give us an equation where we have 2 RT over 2 pi is equal to the square root of m over k. Now, in this situation, when we do this, it's so much harder to forget to square everything on both sides because we can clearly see everything here. We know that our square and our square root are going to cancel on the right-hand side, so I can cross those out. And this is going to give me t squared over, when I distribute that negative, this is going to become, or not the negative, when I distribute the square, this is going to become 4 pi squared, which is equal to m over k. Now, in the previous lesson, I told you about the problem-solving technique where if we want something in the numerator, what we can actually do is on both the left and the right-hand side, we can take the reciprocal. And if we take the reciprocal, rather than having to cross multiply and divide and mix up terms, we can make it look like the following. This is 4 pi squared divided by t squared, which is equal to the spring constant divided by mass. Now, this is really good because look, we have the spring constant in the numerator by doing that simple technique. All I have to do now is multiply up the mass. So this is going to give me an equation of the following. I'm going to get the spring constant is equal to 4 pi squared, which is just a constant, times mass divided by t squared. Now let's plug in all the values. K is equal to 4 pi squared multiplied by the mass, which we converted to 0.200 kilograms instead of 200 grams. And we're going to divide it by that 0.66 seconds squared. Ooh, that S was a little rough, so I'm going to fix that. There we go. Okay, now if I plug in all those values, I end up getting a value of 18.1 newtons per meter. And remember, the spring constant is not a vector quantity, it's not directional, it is a measure of the stiffness of the overall spring, regardless of given position. Now, this is where we go into that question that they asked in the second part of this, and they said, does it matter if this spring vibrates horizontally or vertically? Or does it matter if it oscillates vertically or horizontally? And in short, the answer is no. And the reason is because when we look at our formula, look at the variables that are considered in solving for this period here. First and foremost, we see that we only have mass and the spring constant. So right away, that kind of rules out the fact that we're like, oh, okay, I don't think it really matters if it's vertically. And just to even further emphasize that, what variable is missing in this equation when we're dealing with the period of this or when we're even solving in these situations, it's the gravity. So when we look at this, there's kind of two reasons that we would say no, that it doesn't matter. So I'm going to say no. And the first reason is the lack of gravity. There's no need for gravity, or gravity is not involved in the equation. It has no impact necessarily. Yes, if we were solving for using the spring constant and we were using Hooke's law and we were comparing it vertically, yeah, you're going to see G within this. But when we look at this specifically, no, because G is not required. Specifically, when we look at these two, we're like, oh, okay, in the horizontal and vertical situation, it's the G value is not going to have an impact specifically on this oscillating backwards and forwards given these conditions or given specific conditions. The second piece is the following: the energy is maintained, energy is conserved. And specifically, if energy is conserved, that means that at every single point, we can describe the total mechanical energy as being the same, because they're implying that this thing would complete a certain amount of cycles for a given second, or complete or have a certain amount of seconds per cycle. And so if the timing is conserved, then whether it's horizontal or vertical, the energy is going to be overall conserved because it's completing the same amount of oscillations in a given time period, meaning the same energy is involved here. Now, you could get even more specific than that, and you could really dive into detail on that, but that's just two short reasons as to why that it wouldn't matter if it's horizontal or vertical, we should get the same result for this spring constant. And again, it's a spring constant. So whether it's horizontal or vertical, a third reason could even be that this spring isn't changing. Even though it's hung in a different orientation, it has no impact on how stiff the natural spring would be in terms of its material. Okay, now let's go on to a third example and our third and final example. So when we look at this question, they say that we have a 2.6 gram mass, so a very small mass, that experiences some sort of momentary, or I really want you to annotate this, an instantaneous acceleration. There we go. And I'm just going to short form it as that. So this is an instantaneous acceleration, more importantly, because the acceleration, as we know, whether it's horizontal, vertical, whether it's a pendulum, these things is the acceleration is going to be changing rapidly, and it's never going to be the same unless it's by symmetry onto the left and right. Now, we have this mass that's experiencing acceleration at this momentary, instantaneous point, and then at a displacement of 0.7. So specifically at that displacement, it experiences that instantaneous acceleration of 20 meters per second. What is the K for the spring, or what is the stiffness of the spring, or what is the spring constant? Now, if this is the specific moment or the instantaneous acceleration, what we can look at is the following. Let's assume that this is some sort of horizontal spring. And so I'm going to draw this one out just so that we can have a visual of it in the following way. So I draw this out and I put a spring together as best as I can, and I'm going to make sure it stretches out over to the right hand side like this, and then I'm going to attach a mass here. And maybe I'll shorten the spring just a touch. There we go. And I'm going to draw the mass on the end here. Now, realistically, actually, I should even be more accurate with this thing. We're going to assume that it's a frictionless environment where the mass is actually in contact with the surface and it's oscillating backwards and forwards. It doesn't necessarily have to be in your diagram, but sometimes it helps. Now, we're going to draw the forces on here and things that matter. So first and foremost, here is our equilibrium position where x is equal to 0. And so I'm going to call it the EQP again. This is where x equals 0 meters, or it has 0 displacement. They told us that the distance from here to the mass, or the amount that it's displaced, is 0.7 meters. And so I'm going to make sure I include that in our diagram here. And then in terms of the forces that are on this, vertically, the normal force and the FG are equal. The force that we have is the restoring force, or the Fs, that is wanting to push this thing back towards equilibrium. And so I'll annotate it on the diagram there. There's Fs. If we know that Fs is going this way by earlier instruction, or when we really broke these down, we also said the acceleration follows the net force, and both of these are going in the left direction. So I'll even put that in here. It's either negative or left. both of these two things, the force, the spring force, or the restoring force, and the acceleration. Okay, now that we have a visual of this, we have one force that is dictating this pull or this push back towards the equilibrium, and so it's our net force. And if we put this all together, we're going to say that F net is equal to Fs, and by Hooke's law, it's equal to negative Kx. Now, if this is the F net, remember, the nice powerful tool about this is if the F net is only one force, we can describe F net always as mass times acceleration, which is equal to, by Hooke's law, Fs, which is equal to negative Kx. Now, we're solving for specifically the spring constant here, and so in order to do that, we're going to divide by negative x, divide by negative x. This is going to give us the following, where we have K is equal to mass times acceleration divided by negative x. Now, this brings back a very, very similar thing that we did earlier in class, and it's going to give us two options. The mass, we might need to change this mass very quickly, and that's the following. Instead of writing it as this, we need to divide it by 1,000 because we have the 1,000 here. So when we divide it by 1,000, this is going to make it, or I should say we have 1,000 grams in a kilogram. When we divide it by 1,000, this is 0.026 kilograms. Okay, so this is going to be the mass we use. And so I'm going to scroll down and be like 0.0026 kilograms multiplied by the acceleration. Here's one way we can do this. Which way is the acceleration going? To the left, meaning it's negative. If it's negative, I'm going to plug that into the brackets as negative 20.0 meters per second, because that was the magnitude given to us at that instantaneous moment, divided by negative in brackets. We're just going to put the simple displacement as a scalar value. And then the other way we could write this is the following. So remember, this allows us to cancel the negative, we get a positive or positive K, a positive spring constant. The other way, and the other way I'm going to give you the choice to do this, is you could write it as the mass, again, is the same, 0.026 kilograms. You could leave the acceleration as signless, 20.0 meters per second squared, and then you can divide by the following. Negative, in the brackets, we look at this piece here, and see, this is, I guess, maybe the issue, is that when I look at this, if I assume that this went to the right, this is a positive x value. So in this range, or in this region, this is positive x. And so I guess, yeah, this is where we're going to reach an issue that I didn't even foresee even in doing this example here, is rather than it being compressed where the x would be negative, it's being stretched where the x is positive. So that forces this to end up being the first answer that we did, which is this one here, in order to get that positive x. Or what we're going to have to do is just ignore the negative here. So maybe that's even another option. That's a third option. It's not my favorite, but I mean, it does the trick. We'll still get the same answer. I'm just not a big fan of it, because as we deal with vector quantities, which in this case, the acceleration is a vector quantity, I think that this way is going to be the way that I think a lot of you will tend to go. But in the case of writing the x as either positive or negative, we've seen how this can now give us an issue here. So, I mean, maybe caution away from that and just stick to putting the negative or positive with the acceleration. But I mean, whatever will get you this k as a positive value. Now, therefore, we're going to get a k value of the following. Therefore, k is equal to 0.0743, and this is in newtons per meter. Excellent. There we go. Now, what this implies, when I zoom out on this answer here and I zoom out on this situation, is we have a very tiny mass that's oscillating left and right. And through this oscillation of going left and right, because it's such a small mass, in order to be moving left and right, especially with an acceleration of 20 meters per second, it would have to imply that we have some sort of very loose spring, or a spring with a very low stiffness. And when I see a value like this for K, it is a very non-stiff spring. It doesn't have a ton of stiffness to this. Now, I really hope you go into the assigned questions and work through a ton of these. Reason being is that these are maybe a little bit complicated to get your head around just initially, in terms of solving for K, solving for acceleration, maybe solving for even displacement. The one reason I would even say do the practice problems and do all of them is look at the practice problems we've done in class today. Our K value, we solve for a K value. In the first one, we solve for a K value. In the second one, we solve for a K value. Although we were dealing with all the different problem-solving techniques that we may see in this lesson, it's still not enough to build that mastery around it, because even with all these different techniques, And just solving for K, we've technically exposed ourselves to all the things we need to in terms of vertical and horizontal springs, and even solving for period. But you may be asked to solve for any of these other variables in the equation and just be given the spring constant. So I would say make sure you do all these assigned questions, just make sure you're prepared, and that's going to help you a lot. All right, good luck with the practice.